Hello everyone, and welcome. This video is a presentation of my final PhD defense, and hopefully it provides both an example of what these presentations might look like, as well as a record of what I got up to during my doctoral degree. The title of this dissertation was An Analysis of Primary Stability of Stemless Humeral Implants in Shoulder Arthroplasty. To begin, we'll cover some epidemiology. As we all know, shoulder injuries are very common, especially in the baby boomer demographic, and degeneration of the shoulder joint can be severely life-affecting. Although many injuries heal naturally, shoulder replacements are frequently performed to improve the quality of life of those who are experiencing injury or reduced function of the shoulder. In 2017, over 101,000 shoulder reconstructions were performed in the United States, and using a Poisson regression model, it has been predicted that over 350,000 shoulder reconstructions will be performed annually in the United States alone. Shoulder reconstructive surgeries come in a few different forms, but for conciseness we'll be focusing on the full reconstructions. First, we have the classic anatomic total shoulder arthroplasty. The first full total shoulder with both a glenoid and humeral component was installed in the 70s by Marmer and has fast become a common treatment option for trauma, infection, or severe glenohumeral arthritis. The prevalence of these reconstructive surgeries has been growing steadily, and over 50,000 of these surgeries are expected to be performed annually by 2025. However, the anatomic total shoulder prostheses are somewhat limited, as they require fairly healthy musculature to provide stability to the glenohumeral joint. In the early 1980s, Neer created the first fixed fulcrum design, which reversed the natural glenohumeral articulation, replacing the anatomically convex humeral head with a humeral cup, and the anatomically concave glenoid with a glenosphere component. This new arrangement provides artificial stability to the shoulder joint, and therefore facilitates improved outcomes when a patient's pathology includes damage or disease of the rotator cuff musculature. This more stable design is naturally preferable in an aging population, and has fast outpaced the anatomic TSA design in incidence. Over 300,000 of these prostheses are projected to be installed annually by 2025. Due to the popularity and growth of RTSA use, we have focused on this design as the topic of this dissertation. However, the RTSA design has not been static. Optimization of this prosthetic has been the topic of many works, and over the years we've begun to see a dramatic iterative decrease in the length of the stem component. These shorter stem designs are beneficial as they require a less invasive surgery, they retain a larger volume of good quality bone, and they also result in less dramatic load sharing by the metallic prosthetic, thereby decreasing the effects of stress shielding. Due to its recent popularity and the momentum of the research of the stemless design, we've elected to focus on the stemless RTSA variant, and more particularly the stemless humeral component of the RTSA for this particular investigation. So we'll now begin our story by discussing the clinical pathology that has driven this research. On the radiograph to the right, you can see that there's a large gap on the medial side of the stem. This is an example of implant loosening, where the implant has improperly bonded to bone. When one of these osseointegrating or a cementless implant is installed, it becomes affixed to bone through a phenomenon called osseointegration, where the bony tissue will grow into the porous voids of an implant. However, that process can be inhibited by excessive motion between the implant and the bone, which is a metric called micromotion. The tolerable threshold for this metric has historically been set at 150 micrometers, but that itself is a topic currently under debate. Now, there are two major directions of bone implant relative motion that we should discuss separately. First, we have tangential micromotion, where the implant slides relative to bone. This is resisted by first mechanical interlocking, where the bone has grown into the implant and provides a physical barrier to motion, and second through mechanical friction between the implant and bone. The second direction of micromotion is orthogonal micromotion, where the implant distracts or subsides into the bone. This is resisted by chemical bonding of the bioactive materials to bone, and through eventual interlocking, which occurs when the bone has grown into the implant sufficiently to a point where it can grab the implant and stop it from distracting. This is similar to how Velcro functions. Now, when evaluating implants, we need to have a method by which we can investigate implant performance by replicating the environment that the implant will be exposed to. A common method of doing so is through using computational finite element methods to predict bone implant behaviors and to rapidly evaluate novel designs with low lead time and low overhead. However, these in silico studies are susceptible to modeling error, as assumptions and simplifications must be made before an FE study can commence. Alternatively, one can perform a benchtop study, which is a more direct measure of implant performance. However, before this dissertation, many benchtop studies were very limited in terms of loading protocol and performance quantification method. On a positive note, though, the restrictive limits of existing benchtop studies provided the major research gap which was targeted in this work. Both methods were leveraged for this dissertation. To begin, we should discuss finite element studies. These investigations leverage the finite element method, which involves the discretization of a solid continuum into a finite number of elements, numerically solving field problems described by a set of partial differential equations. These methods are well regarded, but they usually require a number of simplifications and assumptions to be made, making them susceptible to modeling error. There's no standardized method for these evaluations, and the prevailing protocol for setup of these models has been set almost solely through precedent works. In contrast, benchtop studies don't make use of material simplifications and are directed towards replicating the environments being investigated directly. These works make use of bone tissue samples, either from cadaveric or animal donors, or sometimes they use bone analog materials like polyurethane foams. However, these studies are generally limited by the physical designs of the loading simulators involved and can be restricted by sampling system constraints or occasionally boundary assumptions. The methods leveraged in these studies are partially directed by precedent works, but they're also driven by the ASTM F2028 and ASTM F1839 standards, which are focused on the quantification of implant performance. However, these two standards, although technically acceptable, are often misinterpreted, which brings us to one of the driving principles behind this doctoral thesis. The ASTM F2028 standard for the dynamic evaluation of glenoid loosening provides direction to the quantification of implant stability of a glenoid baseplate. However, there is no ASTM standard that references the quantification of humeral implant stability. This document has frequently been referenced in humeral component studies, which is acceptable in theory, but has sometimes led to the gross misinterpretation and misapplication of the methods outlined therein. This is an example of a study that misinterpreted the ASTM protocol when transferring to the humeral side, using LDVTs as outlined technically in the standard, while adding a significant number of confounds to an otherwise straightforward protocol. On the other side of the ASTM standard limits, many of these evaluations that follow the F2028 standard limit themselves to uniaxial planar loading protocols that are simplifications of the true loading state of the shoulder, which, as we now know through the work of the Julius Wolff Institute, is really a complex musculoskeletal structure that's exposed to a significant variety of loading states. These uniaxial evaluations still provide excellent insight into implant behaviors, but they don't necessarily paint a very thorough picture of implant performance. The second ASTM standard that is frequently referenced is the ASTM F1839 standard specification for the use of rigid polyurethane foams during evaluations of orthopedic device performance. This standard essentially provides direction to which polyurethane foams are acceptable as material proxies in lieu of bone samples, but as we will discuss in this work, they may also introduce significant confounds to a testing protocol. So, without stalling any further, we can now discuss our base objectives and null hypotheses. First, before developing an optimized protocol for the thorough evaluation of novel prostheses, we first need to determine what outcome measure to evaluate. Although works have historically leveraged micromotion as an outcome measure, almost none have differentiated between tangential and orthogonal micromotion directions. Therefore, we first wanted to quantify both tangential and orthogonal micromotion in stemless humeral component implants separately. After identifying the driving micromotion mode for the implants under investigation, our second objective was to develop a loading apparatus capable of applying a complex array of physiologically relevant loads to investigate the degree of primary fixation in stemless orthopedic implants. Using the developed loading apparatus, our next goal was to identify the acceptability of using foam analog materials. We employed a press-fit evaluation to determine if the conclusions would be the same for synthetic and animal specimens. Our null hypothesis was that no significant differences exist between foam analogs and animal specimens. Following, we evaluated a clinically relevant surgical variable, neck shaft angle, and its effect on primary fixation. Our null hypothesis stated that neck shaft angle has no significant effect on primary fixation. And lastly, we re-evaluated the effect of neck shaft angle using computational methods. Once again, our null hypothesis suggested that neck shaft angle would not have a significant effect. Now that we've completed our introduction, we can now begin discussing the individual chapters. As noted, our first evaluation focused on distinguishing between orthogonal and normal interface micromotion directions in stemless humeral prostheses. Here, we wanted to identify whether orthogonal or tangential micromotions were more defining in the subtype of RTSA being investigated. We also wanted to split orthogonal into distractive and compressive directions, and we focused on the distractive direction as it's been hypothesized that it poses a larger challenge to implant long-term fixation. In order to identify the subsurface behaviors of the assembly, we employed computational finite element methods for this investigation. The purpose of this study was therefore to quantify both tangential and orthogonal micromotion in stemless humeral component implants. To do so, we investigated two different stemless humeral implants that are available on the market today. These were the Stryker Perform stemless implant and the Stryker Simplicity stemless implant. For our computational model, we used titanium material properties for the implant body, homogeneous cortical bone properties for the cortical bone, and inhomogeneous trabecular bone properties using the Morgan et al. Modulus density relationship to calculate the Young's modulus property of each element. For our boundary conditions, we applied a 700 Newton load to the center of rotation of our implant and Ancaster boundary conditions to the distal surface of our bone body. For our outcome measures, we evaluated micromotion in micrometers, and we segmented our implant into 5 deepening slices split into 36 circumferential sections. We evaluated both distractive micromotion and tangential micromotion separately. The results of this investigation gave us some good insight into not only the performance of the implants evaluated, but also into how we should be investigating these geometries. We first observed that the geometry of the implant influenced the micromotions detected, and more notably that in both of the stemless geometries evaluated, distractive orthogonal micromotion was the more defining metric. In addition, we also noted through our segmental investigation that deeper slice depths experienced lower micromotions. Responding to our null hypothesis, we found that orthogonal micromotion is the predominant micromotion direction in stemless humeral prostheses, and therefore distractive orthogonal micromotion was isolated as the metric measured and reported for the remainder of this work. Subsequently, we needed to design a loading apparatus for our evaluation, as well as a data collection method that would target orthogonal distractive micromotion. Now, existing apparatuses are limited as they predominantly only evaluate planar uniaxial loading states. However, we know through instrumented implant investigations that the shoulder is actually exposed to a much larger array of loading magnitudes and directions than can be effectively replicated using a simplistic uniaxial loading protocol. Therefore, we set out to develop a loading apparatus capable of applying a complex array of physiologically relevant loads to investigate the degree of primary fixation in stemless orthopedic implants. In order to do so, a novel triaxial loading apparatus was designed. This versatile device was designed for the comprehensive evaluation and realistic biomechanical examination and repair of upper limb systems. And for those of you who were diligently paying attention during that long acronym, and perhaps who don't like saying long names, the Cerberus apparatus was created. Now, the premise of this apparatus is simplistic enough. By using a sphere and a system of polished force application pads, a combination of orthogonal vectors can result in a known resolved load passing through the center of a sphere, which can be easily calculated through basic trig. Now, naturally, we wanted to verify that the loads generated by our pneumatic system were accurate to our loading requests, so we did a force calibration using a load cell and a stepwise loading protocol to verify our output loads. We evaluated our system based on the percent difference from the requested load and found that all of our loads were well within acceptable ranges to our output requests. In addition to our loading system, we also needed to design a digital tracking system to measure bone implant relative motion. This system leverages 3 high-resolution machine vision cameras with paired low-distortion lenses, and we utilize a digital tracking software called ProAnalyst to quantify the micromotions detected by our digital system. To verify the operation of our digital system, we used a micrometer, a generic graticule ruler slide, and a 3D printed custom graticule holder. The results of our analyses showed for macro tracking over 2 mm, an average percent difference of 2.18%, a mean squared error of 0.14, and an R-squared value of 0.96 for a linear test. We also evaluated the system at a micro level and found that at a range of 20 microns, the system exhibited a maximum percent difference of 1.45%, no significant hysteresis error, and a coefficient of variation of 0.047. Overall, the findings of this work confirm the successful design and implementation of a novel system, effective in the application of loads in 3 dimensions, as well as the efficacious implementation of a high-resolution digital tracking method for the evaluation of implant distractive micromotion. Now that we had developed a novel apparatus, we could then begin to evaluate implant behaviors in real cases, which brings us to Chapter 4, where we assess the differences in press-fit evaluations using synthetic bone analogs and bone tissue samples. For our background, when performing implant evaluations, a researcher can choose between using real human harvested tissue, bone materials harvested from animals, or polyurethane foam substitute materials. As human bone and animal specimens are essentially exactly the same and have been interchanged during orthopedic evaluations for a long time, we decided to focus on distinguishing between general harvested bone and synthetic foam bone models. Now, harvested bone is an anisotropic and inhomogeneous material, whereas foam analogs are isotropic and homogeneous. This is important in the context of press-fit implants. Now, press-fit implies that a device is slightly oversized for the hole that it is being inserted into. This is a common practice, and it's something that's regularly done in the orthopedic industry, particularly in osseointegrating implants, which is that topic that we discussed earlier. It was therefore the purpose of this investigation to determine if analyses using foam analog materials would give different results to those which used harvested animal bone materials in terms of primary fixation. In order to do so, we designed a custom modular implant with a variable base which would let us control the degree or the magnitude of press fit. This custom implant was press fit into the bone or polyurethane substrate, and a load of 150 newtons was applied at an angle of 45 degrees in mimicry of an eccentric load that would stimulate implant liftoff or implant micromotion. Our high-resolution digital tracking system was targeted at the liftoff point, and this process was repeated for a number of different press fits ranging from 0 mm to 0.875 mm diametrally. Using our system, we evaluated micromotion right at the bone implant interface and tested 3 densities of foam, as well as harvested porcine tibial specimens. Each test was repeated 3 times in each foam analog model and 8 times in the porcine specimens. The results of this study were fairly interesting. First, we found that increasing press fit has an influence on primary fixation. Second, we found that increasing foam analog density influences fixation. Specifically, increasing foam density decreased micromotion. However, this behavior differed in the bone material model, and the foam analog trends were not consistent with the trends exhibited by the harvested specimens in the press fit models. Therefore, employment of harvested bone for the assessment of implant fixation may better represent mechanisms that involve the microfailure of trabecular bone. Next, we wanted to evaluate the hot topic clinical variable of neck shaft angle using our novel loading simulator. Now, when installing a reverse total shoulder arthroplasty, a surgeon needs to decide on the resection inclination or the angle of the humeral head cut. Many resections are done at approximately 135 degrees, which is comparable to the native neck shaft angle. However, a surgical team can also elect to use a different neck shaft angle instead. For this evaluation, we decided to evaluate 2 common clinical neck shaft angles, 135 degrees and 145 degrees. In order to evaluate the performance of these options, we used the previously discussed metric of micromotion, or more specifically, bone implant distraction during loading of the implant. The purpose then was to compare 135-degree and 145-degree neck shaft angles and their effect on component performance in reverse total shoulder arthroplasty implants. In order to do so, we prepared 16 bilateral proximal humeral specimens. Neck shaft angles were controlled using an intermedullary diaphyseal referencing cut guide. The humeral heads were then resected and a trabecular bone bed was reamed and blazed. And then the specimens were implanted with a Stryker Perform stemless reversed humeral component, which is a commonly utilized clinically available implant. In order to effectively evaluate these implants, we also needed to develop a loading protocol. The shoulder really is a complex structure, and it's exposed to a large variety of loading states, enough that we wouldn't be able to evaluate each loading state individually. Instead, we developed a loading protocol which was representative of the worst-case loading states that the implant would be exposed to. The largest eccentricity, and therefore the most challenging loading state, was evaluated at 3 angles which would challenge the implant in different ways. This boundary loading protocol was evaluated at 20, 40, 60, 80, and 100% of the physiological load for 30 cycles at each loading state and at all 3 directions. We randomized the directions to accommodate for any microfailure in the bone. The Cerberus apparatus was of course used for this evaluation in conjunction with 3 high-resolution cameras pointed at the superior, anterosuperior, and anterior aspects of the bone implant interface. For our results, we found that increasing neck shaft angle decreased micromotion. We also evaluated implant biomechanical survivability and found that for all loading scenarios, increasing neck shaft angle also increased survivability. We therefore found that higher neck shaft angles can provide better fixation and survivability. Now that we had established experimental insights into the effect of neck shaft angle, we also wanted to evaluate the variable computationally. As we were not as limited computationally, we could investigate a larger range of neck shaft angles, so we evaluated from 130 degrees neck shaft angle to 150 degrees neck shaft angle in 5-degree increments in order to provide a much more thorough picture of the influence of neck shaft angle. Similarly to the last investigation, we wanted to assess the surgical implantation variable of neck shaft angle and its effect on primary fixation. In order to do so, we began by developing a parametric version of a stemless humeral implant using a Python library called CAD-Query. This implant was positioned into the humerus model in silico, initially at 135 degrees neck shaft angle, and then a matrix transformation was used to vary the neck shaft angle for the remainder of the NSAs under investigation. For this evaluation, we used the same modeling approach as in our previous FE chapter. We had more opportunity to evaluate real physiological loading profiles in the computational analysis, so we evaluated a 30-degree shoulder abduction motion, a 30-degree shoulder abduction with supination motion, a 20-Newton head height lifting motion, and a single-hand steering motion, all of which are loading profiles that could reasonably occur postoperatively. These values were corrected for patient body weight. For this study, we also evaluated bone implant distractive micromotion, and we performed this using a sample size of 8. These plots show the micromotions developed at each node as a heat map, where more green indicates more stability of the implant. Very visually here, you can see that the 150-degree neck shaft angle resection is more stable. To summarize our findings, we found that increasing neck shaft angle decreased micromotions, and for every 5-degree increase, we saw approximately a 17% reduction in micromotion. But just to wrap up this study, we found that higher NSAs can decrease bone implant distractions. Reflecting on the last 2 studies, we can hypothesize that the increased fixation at higher NSAs was a result of reducing the eccentricity, and therefore the challenge of these loading scenarios, and also that by taking a higher NSA cut, you can retain a larger volume of good quality bone, which is a topic that we evaluated in one of our appendices more thoroughly. But I'll hint that we were able to verify the second of these 2 hypotheses, showing that bone density is significantly better at higher NSAs. Of course, those 2 components, when working together, result in significantly better implant stability, which was the overarching clinical conclusion of our work here. Overall, this thesis found that tangential micromotion differs from orthogonal micromotion in both magnitude and osseointegrative effect, and therefore we need to begin distinguishing between these two when evaluating implant performance. Additionally, we found that through a number of different methods, increasing neck shaft angle of a stemless RTSA can decrease the micromotion experienced by that implant, therefore resulting in improved fixation. Of course, I'd really like to thank my funding sources and all those entities which made my research possible. More specifically, I'd like to thank my incredible supervisors and mentors, Dr. James Johnson and Dr. George Athwell, for their hard work and dedication to this project. I'd also like to thank my resident collaborators and my colleagues at the Hulk Clinic. There were many people not directly named here, but I'd really like to stress how this work was not the achievement of one alone, but truly a collaborative endeavor, and I appreciate the hard work that everyone put in to make this possible. And of course, a huge thank you to everyone who took the time to watch this video.